Good afternoon, everyone. My name is Junho. I'm a member of Intel Developer Cloud Networking team. I'm a, I'm a cloud network infrastructure builder and responsible for designing a multi-tenant VPC networking service with Intel IPU for next generation IDC networking. Today, I'm going to introduce P4OVN, a solution to offload OVN into Intel IPU for IDC. For multi-tenant VPC networking service, we have decided to use OVN as SDN controller in IDC because it is open source and widely used in many production environments. So ever increasing the bandwidth demand, for example, the 200 gig networking and even 400 gig Ethernet speed today due to surge AI workload. This requirement derive consideration of hardware offloading for a software data plane from tenant compute host to off-path accelerator adapter like IPU because it is hard to keep up with a speed demand only with software. Previously, back in several years ago, we first built tenant network on top of enterprise network. To isolate network, VXLAN and VLAN from vendor switches are used. This leads to a relatively static configuration managed by central authority, not by a tenant. It limits scale of the network as well. Moreover, this introduces a long provisioning time when new configuration changes are requested, even simple changes in its configuration. The various stakeholders are involved in reviewing these changes to analyze how much it impacts on enterprise network. This new sort of requirement leads us to consider decoupling the tenant networks from provider networks. Now let's move on. This one is the normal Intel legal disclaimer. So before going into detail of P4OVN, let me briefly introduce what IDC is. IDC stands for Intel Developer Cloud, which is a public cloud service launched in September 2023. It gives customer access to the latest Intel hardware and software. For example, the Intel Xeon for CPU, and we also provide a GPU called Ponte Vecchio, and also we provide AI accelerator like Gaudi. For use case perspective, the customer brings their AI model, try out for testing and validating the models on the latest Intel platform before production without burden on capex investment. Here is the here is the link where you can sign up and run your workload right away. From infrastructure service perspective, although the IDC service has an in-house implementation of the CMS side, but underneath core technologies as foundational pillars to run IDC control plane are still open source based. For example, we heavily rely on the Kubernetes cluster for lifecycle management for many applications, and also we use the KubeVirt to offer the tenant for the VM as a service. And also we also heavily rely on the MetaQ and Irony for the BMAS service. So what is the IPU? IPU stands for Infrastructure Processing Unit. It looks similar as a normal Ethernet adapter card, but one big difference is that it is a single system on chip in which multiple components are integrated. As you can see on the left-hand side here, it has a 16-ARM core compute tiles running the Linux kernel, so that it can run any types of the workload. And also it has a PCI Gen 4 to interconnect any types of compute node, such as the CPU, as well even with the GPU or any type of the accelerator up to 4. And also it has underneath this PCI bus, there is a multiple hardware, multiple protocol engine. For example, the RDMA and RDMA for the remote memory access, and NVMe for the storage, and RAM for the host for networking. And also, along with these three hardware protocol engine, underneath there is a P4 programmable packet processing pipeline as well. And also, this pipeline also working with the inline encryption and decryption engine for security. For example, the IPsec is one of the use cases. And also, it has a traffic shaper and a 200 gig Ethernet port. In earlier server architecture, as you might know, that the compute and networking agent used to coexist at the tenant host, but this off-pass IPU introduced a new architecture where networking control plane and data plane components are now moved to the IPU. And then by exposing the SRV and SIOV ports to a tenant workload, so IPU can directly process tenant traffic without software involvement on tenant host. With this new architecture, the benefits are quite obvious. That first, it can save the CPU memory resources on the tenant host side. The second one is that it increased the infrastructure security by adding the air gap to isolate the tenant application from infrastructure application. And third one is it decoupled the ownership of tenants compute from infrastructure compute, like this. So what is the P4OVN? So actually, the OVN is the SDN controller for OVS. If you can imagine that the architecture of the OVN, when CMS create a logical OVN construct, for example, the logical switch and router, and for example, the stateful ACL in a northbound database, the OVN translate this high-level network abstract into a low-level or logical flow in southbound database. Since OVN views multiple OVS in a big logical pipeline, each ovn-controller running on each host that is the same location where OVS run receive a global network state from the southbound database. Then it extract each ovn-controller extract the relevant state for this node, and then at the end it translates this state into the multiple open flows, and then these open flows are installed in the OVS pipeline. So the P4OVN is not a mean of offloading a generic all open pipeline into IPU. The OVN give us quite a broad freedom of logical topology composition with a logical switch or router. For example, it allows to create a series of the logical routers. So from hardware perspective, it is infeasible to implement such behavior in IPU hardware because it requires a multiple packet recirculation, which impacts on packet forwarding speed and line length. Therefore, we should restrict this freedom of generic OVN use case to specific our one IDC use case. So in IDC, we allow a tenant has multiple VPCs, and each VPC has only one router, and also the router has a multiple subnet underneath and static route to route the traffic between different subnets. This restriction allows us to implement implement the distributed virtual router in IPU hardware. So P4OVN is a co-design of IPU hardware and software to implement this distributed virtual router and security groups that are compatible with OVN architecture. On IPU CPU side, which is the ARM core, it still run OVS software data paths. In IPU's programmable packet processing engine, we developed the P4 program called the hardware flow cache here. And also, this hardware flow cache is optimized for OVN pipeline, in particularly the layer 2 and layer 3 of forwarding. And also, the most of the intelligent or stateful packet processing are still left on IPU's CPU. So we developed hardware pipeline with P4 language in the same manner of the software development. Thanks to P4 language and its programming model called P4 runtime, we can easily develop the high-level API to be used by an upper layer application, for example, the ovn-controller in this case. Or any types of the SDN controller can be integrated with this API to program this hardware flow cache here. Although the P4OVN hardware flow cache still follow OVS cache architecture, it is not meaning of offloading the OVS software cache, for example, the micro cache and megaflow cache into the IPU. So actually, there are multiple regions. It is not straightforward to offload OVS software cache into the hardware. The first region is that in the OVS connection tracking action. Actually, it requires a stateful connection tracking for stateful ACL and not in load balance use case. So actually, this requires the hardware keep track of the flow state transition in terms of a flow state machine. It is so complex and hard to achieve the high speed of packet processing at the same time. Rather, the hardware is much more specialized for forwarding a packet in stateless manner. The second reason is that the OVS recirculation action. The hardware cannot recirculate the packet indefinitely due to the performance reason. The packet processing in hardware is full, and also the packet processing in hardware is full of the memory transaction to look up the table and execute action, which leads to memory latency. In IPU, it allows 2 or up to 3 recirculation allowed. So to overcome these challenges, we design a hardware flow cache consisting of mainly 2 parts. One is the 5-tuple based flow cache table in here, and second one is the forwarding relevant table in here. So every first packet of new flow first look up this flow cache table, and if the table miss, then first packet is sent to IPU CPU, and rest of the packet processing is done by the OVS DPDK or OVS VCHD pipeline. So once it is fully processed by a series of OVS table, usually pre-populated by the oven, which is the ovn-controller here. The flows are new flows are offloaded into the flow cache table here, and then the subsequent packet of the flow will hit this flow table, then go directly through the hardware flow forwarding table here, which is the implementation of OVN, L2 and L3 forwarding. The table in hardware, these hardware forward are usually the pre-populated, as I mentioned earlier, are pre-populated by the OVN, which is the ovn-controller, via this P4OVN API, when OVS tables are usually populated here. At this point, no longer a software data plane, no longer the software data path is involved for this flow processing until the entry in this flow cache table will be edited. But still there is a challenge to implement this flow cache because it actually requires the high insertion rate, which is almost the same as the line rate, and also this flow cache table provides a timer-based for the entry management. But control plane programming path, for example, the P4OVN API, it is not good choice to do that. To address this issue, we devise in-band table management mechanism to insert these entries of the new flow in the flow cache table here. It is auto inserted via a data plane path instead of using the control plane path like a P4OVN API. So, for example, if OVS see the TCP SYN flag, it triggers auto insertion of a new flow entry in the flow cache table. And if we look at the TCP SYN flag, then it expired the entry of the flow to be edited. So now we can achieve line rate flow cache table insertion by using this mechanism. So all these hardware pipeline definition and packet processing behaviors are defined in the P4 language, and we developed the P4 program, and then this P4 program is compiled by the P4 compiler, then embedded in our hardware packet processing engine IPU. Now let's take a look at how hardware flow cache works with some scenario. For example, the intra-subnet communication, and the second one is the inter-subnet communication, and third one is the most interesting part is that the floating IP use case. So let's start with intra-subnet communication use case first. Next a few slides, I will assume that the flow cache table is populated by the first packet of a new flow, and also the hardware flow for table in hardware for table in flow cache table are properly populated by the ovn-controller when logical entities are created by the user. Let's take a look at the tenant A here. In this diagram, the tenant A create a subnet by using the logical router here and logical switches in oven. And three VMs are created and under this subnet. As soon as logical topology is created, the ovn-controller insert the entry in L2 forwarding table in the IPU hardware with the MAC addresses of the VMs. In this example, there are three entries are populated in the hardware. One for each the MAC address of each virtual machine. In the case where two virtual machine, for example, in this case, the VM1 and VM2 are reside on the same IPU here. The communication between these two VMs happen locally. So as you can see here, the VM send out the packet toward the VM2 here. In this case, the destination MAC address of this packet is the VM2 MAC address. So it will look up the L24 table in hardware, and then find the destination MAC address of the virtual machine 2, and then hit. Then as you can see, the action is sent to local because this VM is reside on the same machine. So the packet is forwarded to the virtual machine 2. But in the case of the two VMs are reside on the different the IPU node. In that case, the table matching is same. It used the same table, but the action is different. So in this case, the action is the send to remote. So in this case, after matching on this table, then you will this package should be delivered to the remote IPU node. So for that, we need to encapsulate this original packet with the GNIP protocol. In the case, the GNIP table will be involved to encapsulate the original packet with the GNIP with some metadata driven by the oven itself, and then send this GNIP packet to the remote IPU through the underlay network. After that, this packet is encapsulated, then look up the L24 table again to find the destination MAC address for the virtual machine 3 here. Now let's take a look at the tenant B case. So tenant B create now two subnets, and these subnets are connected through a router. And VM4 and VM5 are in different subnets respectively. So ovn-controller now populate entry in IPv4 table in this case with the IP prefix and next hop ID. So once virtual machine 4 send a packet, this packet's destination MAC address is the router interface. A router interface MAC address of the local router here. So you first look up the RMAC table, and this so the RMAC table is hit. It enabled the IPv4 table lookup instead of the looking up the L2 table. Finally, it is routed locally. Then look up the ARP table to find the MAC address of the target VM here, which is the VM5 here. Usually these R table are run by the machine learning mechanism implemented in the OVS. So whenever the R packet is seen by the OVS, then OVS will automatically populate this table through the P4OVN API actually. And then the ARP table is done, then if the destination MAC address of the virtual machine 5 is found, then the IPU will rewrite this destination MAC address with this ARP MAC table, and then it will finally look up the L2 forwarding table and then send to the remote IPU here, and then the GNIP packet will be delivered to the remote IPU. Then GNIP table will decapsulate the table, and then finally look up the L2 forwarding table again, then find the virtual machine 5 here. Now let's look at the third scenario case. So actually, I think this is a much more interesting use case where many virtual machines communicate external service outside OVN via gateway node, and it's public route over IP. This use case require SNOT capability on the gateway node. For this, we use distributed gateway ports in OVN, and this distributed gateway port is the logical router port that is especially configured to designate one distinguished chassis. In this case, this gateway node. And in Oven, this node called as the gateway chassis for centralized packet processing, and the traffic is rerouted to this selected gateway node, which is usually connected to external network outside open here. So as the lookup is same as the previous use case, which is the inter-subnet use case, until the next hop table lookup. So instead of look up the AIP table in this case to find the destination MAC address, IP and MAC binding, within the OVN, you look up the redirect table, and then find the remote gateway node, and then encapsulate this original packet with the Junho protocol, and then send to the this centralized gateway node. And this node is the software OVS packet processing pipeline programmed by the ovn-controller. Then once the packet received by this OVS pipeline, then the rest of the egress pipeline of the S3 routing data paths are executed. Then find the egress port, which is connected to this external network. Okay. The last one use case is the use case where a centralized gateway is not proper sometimes. For example, the storage traffic use case. The connecting to the storage services outside this OVN network, overlay network. For this type of traffic, the centralized gateway node becomes a single point of traffic aggregation and becomes the bottleneck. So this node cannot keep up with the aggregated storage traffic, for example. So for this case, the traffic should be processed locally usually. To address this, P4OVN support the floating IP and one-to-one NOT capability. It also uses the same mechanism of distributed gateway port in OVN. So, but one thing difference with the previous one is that instead of dedicating the distributed gateway port to a remote gateway node, it set this port to a local IPU here. So in order to expose this the hardware flow cache to the upper layer application, we look at the two types of the API model to expose this capability to the upper layer application. One is the RT flow API. So actually, in this case, the RT flow API is a generic flow offloading mechanism in DPDK ecosystem. But this is usually the good for offloading the open flow expression into the hardware. But if the match and action is not implemented in the hardware, then it usually fails to offload this open flow rules into the hardware. So in order to address this issue, we devised the P4OVN API. This is more the semantic aware API and much more explicit to open pipeline. For example, this API provides a logical flow, a logical switch and logical router and ACL, something like that. And also, this API is much more hardware friendly for optimization purpose. For example, so this is the example of the how P4OVN API looks like. So as you can see here, if the ovn-controller create a logical switch, in this case, the P4OVN API define the create vSwitch API with the vSwitch ID. And if the ovn-controller create a logical router, then for this P4OVN API define the create pre-router and create a virtual router interface, something like that. But this P4OVN API is not yet a common API for in the OVN community, but it still requires a common vendor agnostic API. For example, the ASI is the good reference case for the networking operating system ecosystem. So by using this common and vendor agnostic API, we want to hide the different implementation and hardware characteristic across different vendors, so that any types of the smart NIC and DPU are introduced underneath, then the ovn-controller still work with these types of the hardware at the end. That is our goal. Okay, now let me show you some simple demo. So for that, I prepared this simple logical topology. So in this case, in this diagram, as you can see here, there are two IPU already, and each IPU has a different number of the virtual machine. For example, the one IPU has two virtual machine called the VM1 and 2, and this VM1 and 2 are connected to the logical switch here, and this logical switch is again connected to the logical router. Then this logical router also connected to the external logical switches. At the end, this logical external switch is connected to the external TOR switches through the VLAN 400 for example. And also the outside the open domain, there is a storage servers on the this VLAN 600. Okay. Okay. So actually, as you can see in this screen, there are two IPUs are actually connected to the Kubernetes cluster and managed by this cluster. And also, as you can see here, the Open Center, which is consisting of the two components, the northbound database and southbound database, are also managed by the same Kubernetes cluster for this demo. Sorry about that. Yeah, I'm not quite sure why this playback is not forwarded. Let's see. Let's figure out that. Okay. Let's keep it playing. Yeah. So here, this screen shows the initial state of the Open Center. So as you can see here, there is nothing open constructs are populated in the northbound database. However, in the case of the southbound database, there are two IPUs are connected and one x86 software OVS. The software OVS running on the x86 server are connected to the southbound database. And let's keep playing. Now I'm trying to create a logical topology as I illustrate in the previous slide deck. So we're gonna create two logical switches, and these two logical switches are connected to the logical router. Now, so as you can see here, I'm now creating the two logical switches called the S0 and S1, and then connect the three virtual machine into the SG. Two VMs are connected to the S0, and one VM is connected to the S1 logical switch. Oops. How would I forward this one? Yeah. Let's try another one. Okay. Okay. So now I'm trying to create a logical topologies as I illustrated in the previous slide deck. And now I'm gonna create two different virtual machine on the single IPU device. Then trying to communicate between these two virtual machines. And actually, these two virtual machines are connected to the same subnet. So in this case, we'd like to demonstrate the intra-subnet use case. So in order to generate the traffic, I'm gonna use the ping application to send out the ICMP packet between these two machines. Yeah. Now, as you can see, the ping works in the case of the intra-subnet. Now, let me try to demonstrate the inter-subnet case, which is the virtual machine 1 and virtual machine 3 are reside in different subnet. So for this demo, I'm gonna also use the ping application to generate the ICMP packet. So as you can see, the ping is work as well as expected. And also, this is the highlight of the demo. So as I mentioned earlier, that in order to access the external service outside the OVN, usually the virtual machines are assigned with the floating IP and a MAC address, so that this floating IP could be routable outside the network, outside the open domain. So for that, I create first I create a static route to route the, for example, in this case, the 60.10.10.0/24 IP prefix, and then next hop is the 40.10.10.1, which is the IP address of the TOR switch. An external router. And also, I'm trying to create the SNAP and DNAT rules in order to change the source IP address of the logical virtual machine, which is the 192.160.10.10. And this logical IP address is actually associated with this virtual machine 1. And also the one, whenever this packet is routed to the outside network after source NAT and DNAT, then the MAC address of this virtual machine also need to be rewritten with this MAC address. And now, so in this case, in order to generate the traffic, I'm going to use the iPerf application. Now, yeah, it's almost finished. Yeah. So now first I run the iPerf 3 server on the server which is connected to the external network, which is on the VLAN 600. And on the client side, I'm gonna send out the iPerf traffic, which is the TCP traffic, to the server in this case. Yeah. So this is all I have today for the demo with the IPU. And thank you. And I'd like to also introduce my next topic, which is the open at IDC scale, which will be held on this place. Thank you. Thank you for listening.